Hello, welcome to the next video in a series I'm calling Transformations of Random Variables. And here we're going to look at what I call the sums and ratios of exponential random variables. And so if we let x1 through x3 be IID exponential distributions with lambda 1, that means the density is this, for x is greater than 0. And we have, so this is R3 space, and so we're going to map that into R3 space. These y1, y2, y3 variables defined as this. Now, in this transformation, we need to find the inverse functions of this. So, and what that means is, and I commonly term backsolve for x1, x2, x3. And so the way that this can be done is, here we know that this is y3, so this is y3. Then if you multiply it up, y3 and y2 is this. So you can substitute y2 and y3, multiply it over, and then you have x1. And then x2 and x3 can be done similarly. You just move things and substitute. Now the Jacobian of this transformation is you take this variable, derivative with respect to y1, with respect to y2, with respect to y3, and then you take the derivative of this respect to y1, 2, and 3, and then the same way here. And then this derivative is, I'm going to go through the math sort of quickly, because I think if you're watching this video you probably understand derivatives. But what I do is I take I use this column to use the derivative. So it's this times the derivative of that, which is what this is. Then it's minus this times the derivative of that, which is this. And then it's 0 times the derivative of this, which drops out. And that's why I picked this column, because it's a little bit easier. Now to simplify, we multiply out, and we get this. Then it simplifies to this. I'm going to skip the algebra, and then it ultimately those cancel and it skips and it simplifies to this. So this is the derivative of, or the Jacobian of our transformation. Now what that means is we also let's see what I say. Well, I don't say anything. So, we're going to find the joint distribution of y1, 2, and 3. And we're also going to find the marginal distributions of y1, y2, and y3. And because of that, we need to integrate out the other variables. And to do that, I always like to envision the region that we're integrating. And so here, this is the original x1, 2, and 3. And this is the space. And they're exponential distributions, so they're all positive. And so the boundaries are these side planes between these axes, and this between that, and this between this. So what I want to do is map boundaries to boundaries, and that helps you envision what is going on over here. So boundary 1 is this region, so x3 is 0, and x2 and x3 are allowed free range. And so then this boundary is mapped to this side boundary. So it's the boundary on the right. And it's bounded by x2 equal 1. And it actually goes, like this. Okay. And then this plane or boundary is mapped to the this side. So it's a plane, and then it actually goes forever, but then it's cut off by that. And then this boundary is mapped to the back of this cube that we're creating. So it's this boundary. Okay. So now so these three boundaries are mapped to the three sides of the cube, and then this boundary is by default because each of those have to be positive the way we transform them. So you can see the boundary here, and it goes up. So it's a it's a rectangular object. And so now let's find the joint density of y1, 2, and 3, and that means plug in into the f1, 2, 3 density of the variables that we back solve for. And so that means plug in these for x1, x2, and x3, and that's what those are, into the f distribution. And they're independent, so you can just break them up, and they're exponential with lambda 1. So you just plug in those values, and there's the absolute value of the Jacobian. Now those simplify to this, and here's our regions that we just determined. Now to find the density for y1, we need to integrate out y2 and y3, and y2 goes from 0 to 1 and y3 goes from 0 to infinity. So you integrate this out, and then there's no oh, there's y2. No, there it is right there. So then I'm looking through a little screen so I need to look down at the paper sometimes. So then you know, to take the derivative with respect to that, it's 1/2, and then y2 squared, evaluated at these limits, it becomes this. Then we integrate with respect to y3, and which is, oh, this variable, and here it is, this is actually a distribution, so which is a gamma distribution, and so this integrates to 1. So alpha is 3 and beta is 1, and then that's 2, so that's 2, so that's how it integrates to 1. So the density for y1 is 1 over the range of 0 to 1, so it's actually uniform. Now the density for y2, we integrate over y1 and then y3, and there's no y1 in here, so then the antiderivative is just y1 evaluated at 1 and 0, so that's an easy thing, it just becomes this. And then to integrate with respect to this ends up being a gamma minus the constants out front. So if you divide and multiply by the right constants, then that integrates to 1, which we're left with this, which is this distribution. And that actually ends up looking like a beta, with alpha equal to 2, beta equal to 1, between the range of 0 to 1. And then to evaluate f3, we need to integrate out y1 and y2 of this distribution, and you integrate out y1. Well, there is no y1, so the antiderivative is just y1 evaluated at 1 and 0, so that becomes an easy derivative. You take out the constants for y2, then that becomes 1/2 y squared evaluated at 1 and 0. You just get a 1/2, which is what this is, and we're finished from 0 to 1. And this that looks like a gamma distribution with alpha equal to 3 and beta equal to 1. So one note is that you can take the original density and multiply by these marginal multiply each of the marginal distributions to obtain the joint density back. So that implies that these three variables are independent. And then, as I mentioned in the talk, y1 is uniform, y2 is beta, and y3 is a gamma. And that's all I have for today. Hope you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.